depend at all on X or Y, other than through small black box circuits, which they can simulate in a cryptographic fashion.
Question.
Yeah.
So you're describing this more in terms of the sort of syntactic structure of X, but presumably the name of the game here is something about the semantic structure of X, right? Because of F, I'm sorry, yeah. Because it's pretty easy for Bob to learn X by if the F happened to be the first projection of a pair.
Right. So what we mean by this is that they don't learn anything else other than what they can infer from the value of F itself.
Right. Okay.
So in the end, it's like we do that. So at a high level, the way that typically these cryptographic protocols go is that we're going to simulate a circuit. And we're going to do this using encrypted information so that both of us keep verifying that every AND gate is done right, every OR gate, every NOT is done correctly. We're all assured, everybody, both sides are assured that everything's being done correctly in each of those gates, but we don't know what the values are. We don't know if they're ones or zeros. Till the very, very end, when you reveal your cryptographic keys, I reveal my cryptographic keys in a way that we both have been learning the value of f of x, y, but we didn't learn any of the stuff that happened before that, provided that the gates themselves were executed in a data-oblivious fashion. So that's why we have to use a data-oblivious algorithm to simulate in order to then do this computation cryptographically. The only thing you learn is what you can infer from the value of f itself. Everything else is kept private. And again, I'm not going to be talking about secure multi-party computations. There's actually a follow-on paper that I'm collaborating on with Kevin Du at Syracuse on how to use this algorithm in that context. Today I'm just going to focus in on the sorting algorithm itself. But this is the motivation of why we're studying this 50 years later. Okay? So let me just do a quick review, if you will, of some of the existing algorithms that impinge on the issue of oblivious sorting. First, just to quickly highlight that there's a number of simple optimal but not oblivious algorithms that we teach to people in our data structures classes. Heap sort, merge sort, quick sort, bucket sort, all these are optimal in terms of the running times, but none of them are data oblivious. They all are going to make choices in the algorithm that depend on data values. Similarly, there's also some simple oblivious but suboptimal time algorithms. Hopefully bubble sort, none of you learned, except on the streets, playing dirty with your friends. N squared. Then Badger's sort, odd even merge sort, and Pratt's version of Shellsort with bubble passes. You don't have to use insertion passes necessarily. I'm going to talk a little bit more about that later. Each of these three algorithms run in n log squared n time. So they're not still optimal n log n time. But they are simple and they are oblivious. And then finally, I should highlight that there are oblivious and optimal, but definitely not simple algorithms that exist. The most famous of which is the so-called AKS sorting network, the Einstein-Kumlars and Semoretti, and the Leighton-Claxton hypercube sort, which is based on using AKS together with some randomization as well. Neither of these could be considered simple in the absolute sense. Indeed, AKS, even the constant in the running time, people have gotten it down to like the hundreds of thousands, I think. When it was first published, the constant in the running time was 2 to 100. N log n total time, with a constant of 2 to 100, which is more than the number of atoms in the universe. So it's hard to imagine when that would actually ever become practical. But that really was a beautiful result that showed you could sort obliviously in n log n time. And that was the first of its type.
Is that a deterministic algorithm?
Yes. Yes. So the AKS sorting is deterministic. Leighton-Claxton is somewhat more simple, but theirs is randomized, as is mine. Any other questions before we go on? Just an observation a little bit about oblivious sorting and its relationship to what are known as sorting networks. Any oblivious sorting algorithm can itself be viewed as something called a sorting network. And a sorting network, the way that we view the algorithm is proceeding is if we imagine that there's a wire where each of the inputs will be given in the standard input order, and then pairs of these wires will then be connected, and across those connections we perform a compare exchange obliviously. And the intent is that in the end, the output at the other end would be those same values now in sorted order. So here's just a very simple, small example of using the Pratt's sequence, all powers of 2 and 3, and products of those numbers. But now with bubble sort passes, so just do one pass of bubble sort using that offset, guaranteed that it will sort obliviously your input sequence. Albeit in n log squared n time, not n log n time. Because there's log squared n such products. Okay. So it turns out that Bob Sedgwick used to be a faculty member here. Many of his students have studied the Shellsort algorithm, written an excellent survey on the subject, and noted that there's actually a number of different oblivious versions of this algorithm that you can design. It just all depends on, instead of using insertion sort to sort for every possible offset value, instead you come up with a good offset sequence, number one, and number two, instead of doing insertion sort, do a bubble sort pass. Just compare exchange in a row, all those guys going up. Or do something that they call a shaker pass. Shaker pass is 2 bubble sort passes, one that goes up the sequence, and then another one that comes down the sequence, going up and going down, like a shaker. And then they also talk about something that's known as a brick pass, where you have an alternating bubble sort pass where it uses offsets that are at even offsets, even multiples of the offset, and then at odd additions of that value. So it's sort of the way that bricks are laid down in a standard way in this offset fashion. So they refer to that as a brick pass. And any bubble sort, any shell sort that uses these components to process one of the offset values will naturally be oblivious, because none of these passes depend at all on input values. You're just doing a compare exchange in a completely oblivious way with respect to the input. Let's see that? Okay. So what I show in this paper is a simple randomized shell sort algorithm. It has an oblivious version, which was the main focus that I was trying to look at, that always runs in n log n time. It's very simple, and with very high probability, it sorts. The proof that it almost always sorts is non-trivial, and I'll only be able to sketch at a very high level how that goes. But I'll be able to explain in full detail the algorithm, because it's very, very simple. And then there's also a non-oblivious version of this, where you simply run this, test to see if it works. If it does, you're done. If not, do it again. And so you convert what would be known as a Monte Carlo randomized algorithm into a Las Vegas algorithm. And now you can say it runs in n log n time with very high probability, but always sorts. And then this would be the first shell sort version, or version of the shell sort algorithm to achieve that optimal running time. All right, so let me focus in a little bit on what is the central component of my algorithm. It's very, very simple again. The idea is that we're going to be dealing with regions that are of the size of whatever our offset value. In our case, they're just going to be all the powers of 2, nothing fancy. In the standard shell sort algorithm, if these were the regions that we were dealing with, we would just do an identity permutation between 2 adjacent regions and do any of our compare exchanges between.
What do you mean identity permutation? I keep getting confused by that. Permutation, an identity.
F of x equals x.
Okay, but they're going between different sets.
Yeah, so if this is x, this is in terms of the indices.
Oh.
So it's just do that. Just
So
line
one
up.
goes to
1 goes to 1, 2 goes to 2, 3 goes to 3, 4 goes to 4. That identity permutation.
So there's only
There's only one.
Yeah.
Yeah.